Section 8.2, we're going to start to look at series. And as we start to think about this first definition here, you see this big Greek capital letter sigma, that's notation for taking a sum. So we're taking an infinite sum. So a sum of the sequences that we talked about in 8.1. So this definition here, we start with our lower index as k equals 1. So we sub 1 in for k, and that means we start at a sub 1. That big Greek letter sigma is telling us to add, and then we change k to 2. And then add that 2, now sub in k equals 3. And so on, and you would keep going until you reach that upper limit of integration, but in this case it's infinity, so we're going on and on forever. All right, so it's very different than a sequence in the last section. I'm not just looking at the collection of points and maybe like what do those points approach. That's a sequence. Now I'm adding up those points. I'm trying to decide, does the sum of those points, is that converging? So it's still the same question of convergence. So I'm going to go out of order here before I kind of go back up and formalize some of this. I want us to think about, because I think the formality is rather intuitive. So let's take a look at this first example here. And we are looking at, it is this sum as k goes from 1 to infinity of 1 over 2 to the k. So the first thing I want us to really notice here is the difference between the series that is being denoted here versus the sequence. So the first thing I'm going to kind of do here is I'm just going to put this in parentheses. And let's say that versus if we were back in 8.1 and we were just looking at the sequence, 1 over 2 to the k. So that sequence is simply 1/2, comma, 1 over 2 squared would be 1/4, comma, 1 over 2 cubed would be 1/8, comma, 1 over 2 to the 4th would be 16, comma, dot, dot, dot. And we know that that sequence, so then we would say, because, so we know that because the limit as, I guess I should say k, goes to infinity of 1 over 2 to the k goes to 0. 1 over something going to infinity will go to 0. So that implies that this sequence converges. Sorry, I keep hitting my eraser down here accidentally. So this would imply that this sequence, okay, so the sequence 1 over 2 to the k power, that sequence converges, but it converges to 0. All right, so that's like an 8.1 problem, looking at just that collection of points and what, if any, are those what value, if any, are those collection of points approaching. So here, though, we have something very, very different. So in this example, so here, when we are looking at this sum from 1 to infinity, we are looking at now what happens to the sum of those terms. Okay, these are very different questions, and I just want to get that emphasized straight away. All right, so that is what we are looking to decide, is this converging into some finite value? All right, well, what would we do? I haven't taught you anything about this yet. Well, what might you do? I think the pretty intuitive thing is like, well, let's just try to add up some values and see what happens, right? If we were in class back in the good old days, I might ask you to just kind of think about it. And what does everyone do? They go to their calculator and they start adding up some numbers. Now, what they're looking at, sometimes I have to solidify that a little bit, but adding up some of these values is super intuitive. So let's think about something here. So if I only added up the first number, well, that wouldn't be very exciting. That would just be 1/2, so that's not too exciting. But then what happens if I add up the first two numbers? So suppose I add up the 1/2 and the 1/4. Okay, well that would put me at 3/4. So if I add up the first two terms in my calculator, okay, what happens if I add up the first three terms in my calculator? Okay, that ends up being 7/8. What happens if I go to the first four terms in my calculator? Well, that ends up giving me 15/16. What happens if I add up the first, getting tired of writing all these, I'll tell you that much, 5 terms, so adding the 1/32 to that group. So that would put me at 31/32. And I guess because the directions here, which I haven't paid the least bit of attention to yet because I'm having us do this before we talk about the vocabulary. So if I added up the first 6 terms, which is kind of what our directions are indicating, I would get to 63/64. So let's think about this for just a second. So add up the first term, add up the first 2, add up the first 3, the first 4, the first 5, the first 6. So we're thinking about adding up, but adding up more and more terms every time, and we're really looking at what is this sum? What does it look like it's doing as I add up more and more terms? So as the upper sum, it's indicated to go to infinity. So as I keep adding up more and more terms, what does it look like this sum is going to? So what we just did here, those are called the sequence of partial sums. Or this is called, what's highlighted in yellow, this is called the sequence of partial sums. Each of these values are called the nth partial sums. So those get denoted. So this kind of intuitive thing that I would see students do in their calculator in class, like let's just add a bunch up and see what it looks like it's going to. We can formalize that intuition. We call these the nth partial sums. They get denoted with a capital S and then whatever n terms you're adding up. And so now what we're looking at here is what is happening to this sequence. So what we look at here is what is called, if I can write, the sequence of partial sums. So that's what these are. So what does it look like these are going to? 1/2, 3/4, 7/8, 15/16, 31/32. Doesn't it kind of look like these ratios, these fractions here are getting closer and closer to 1 as we go on? We could do more if we wanted to. But I would say at this point, and we'll be able to prove this by the end of the section, I would say it looks like, without getting too formal here, it looks like this sequence of partial sums, I would say it looks like this is converging to 0. So I would say it looks like this sequence of partial sums is converging to 0, and so it looks like this infinite series, the sum as k goes from 1 to infinity of 1/2 to the k, it looks like this is converging to 0. I'm sorry, converges to 1. I was looking up above. I was just getting ready to make a big comparison here with what we talked about with what I wrote in red, and I fell prey to my own cautions. So it looks like this is converging to 1. Doesn't it drive you crazy when you see me making a mistake and you can't yell at me through the video? So here's the thing. The sequence, what we did in 8.1, just the collection of points, that was converging to 0. But if I add up all of these values, it looks like that, and we'll formalize the looks like, it will be true, that sequence of partial sums is converging to 0. So we have a few things that are synonymous here. The sequence of partial sums converging, and if I just said 0 again, I'm so sorry, converges to 1. That's the same thing as saying this infinite series we have is converging to 1. All right, so let's scroll back up here and just kind of formalize some of this language here. So the nth partial sum is capital S sub n, and that just says add up just the first n terms, whatever the n might be. Okay, so that's the nth partial sum. So that plus a sub n. All right, so what we just did down below here, kind of everything that's highlighted in yellow, if we go back up to this nice summary box, what we're seeing is that if the sequence of partial sums converges to S, then that was saying that this series, that sum from 1 to infinity of the a sub k, that sum is equal to S. So that series converges, it converges to S, S is equal to the sum. So all of those things are saying the same thing. Now, if all of these values we have been looking at here, highlighted in yellow, hadn't been converging to 1, then we would say that the series diverges. So if that sum goes to infinity, or if it doesn't exist, then we would say that the series diverges. So if the sum is equal to infinity or doesn't exist, then the series diverges. All right, so let's look at a quick example of something like that to wrap up this first video here. So if we look at the sum as I goes from 1 to n k from 1 to n of negative 1 to the k. So we start at k equals 1, that would be negative 1 to the first, which is negative 1, plus negative 1 to the second, plus negative 1 to the third, plus negative 1 to the fourth, and so on, right? So let's just first kind of get an intuitive sense of what we're looking at here. And we saw in the last section how negative 1 to the k, or negative 1 to the k plus 1, or k minus 1, gives us that alternating thing that happens, the 1, negative 1 idea. But now we're not just looking at 1, negative 1, we're adding them. So what we want to do is think about the sequence of partial sums. That's kind of all we have at our disposal as of right now, is the sequence of partial sums. So what happens if I just look at adding up the first term? It's negative 1. If I add up the first two terms, I get negative 1 plus 1 is 0. If I add up the first three terms, I have negative 1 plus 1 minus 1. I'm back to negative 1. If I add up the first four terms, and now you're getting a feel for it, right? I'm back at 0. So what's happening if I add up the, first 5 terms, I'm going to be back at negative 1. So if I think about this sequence of partial sums, I'm looking at what's happening to this sequence. And so if we take a look at that sequence right here, so again, this is our sequence of partial sums. That sequence of partial sums is negative 1, 0, negative 1, 0, negative 1, dot, dot, dot. That sequence of partial sums diverges. So if you were, we had a couple of ways that we, in the last section, we would talk about why that's the case. If you have, with sequences, if you have two subsequences that converge to different values, like here the subsequences of the odd terms go to negative 1, the subsequence of the even terms go to 0. When the subsequences converge to two different values, then your sequence diverges. So this sequence, again, sequence of partial sums, diverges, so therefore this series diverges. So these are saying the same thing. All right, so we're going to wrap it up on this first video. When we come back next time, we're going to look at something called a telescoping series.